You are about to embark on a wavelength image voyage out to the end of the universe. Marco Polo journeyed east, Columbus west, but you will travel outward away from your home on Earth, out past the moon, sun, and other planets, past the stars you see in the evening sky, and past billions more that can be seen only with the aid of the largest telescopes. You will journey through great whirlpools of stars to the most distant galaxies visible from Earth. Then you will continue to be carried only by experience and imagination, looking for the structure of the universe itself. Imagination is your key to discovery. It will be your scientific time machine, transporting you into the past and into the future. Go back to watch the birth of the universe, the formation of the first stars, and the origin of the sun and Earth. Then rush into the future to see what will happen when the sun dies and Earth withers. Although you will discover a beginning to the universe, you will not find an edge in space. No matter how far you voyage, you will not run into a wall or a limit beyond which you cannot go. Rather, you will discover evidence that our universe may be infinite, that it may extend in all directions without limit. Such vastness may dwarf our earthly dimensions, but not our human curiosity and imagination. Astronomy is more than the study of stars and planets. It is the study of the universe in which we humans exist. You and I live on a small planet circling a small sun drifting through the universe, but astronomy can take us beyond these boundaries and help us not only see where we are in the universe, but also understand what we are. You have a right to know these things. Perhaps you have a duty to know them. Do not be humble. Although astronomical sizes and distances may dwarf you, remember that you are an intelligent creature and you are capable of understanding your universe. It is, after all, yours. Astronomy will introduce you to sizes, distances, and times far beyond your usual experience on Earth. Your task in this chapter is to grasp the meaning of these unfamiliar sizes, distances, and times. Believe it or not, the solution lies in a single word scale. In this chapter, you will compare objects of different sizes to grasp the scale of the universe. Let's begin with something familiar. Shows a region about 52 feet across occupied by a human being, a sidewalk, and a few trees, objects whose size you can understand. Each successive picture in this chapter will show you a region of the universe that is 100 times wider than the preceding picture. That is, each step will widen your field of view by a factor of 100. In your field of view widens by a factor of 100, and you can see an area 1 mile in diameter. The arrow points to the scene shown in the preceding photograph. People, trees, and sidewalks have vanished, but now you can see a college campus and the surrounding streets and houses. The dimensions of houses and streets are familiar. This is the world you know, and you can relate such objects to the scale of your body. You started your adventure using feet and miles, but you should use the metric system of units. Not only is it used by all scientists around the world, but it also makes calculations much faster. If you are not already familiar with the metric system, or if you need a review, study Appendix A before reading on. The photo is 1 mile in diameter. A mile equals 1,609 kilometers. So you can see in the photo that a kilometer is a bit over 2/3 of a mile, a short walk across a neighborhood. The view spans 160 kilometers. In this infrared photo, the green foliage shows up as various shades of red. The college campus is now invisible, and the patches of gray are small cities, with the suburbs of Philadelphia visible at the lower right. At this scale, you see the natural features of Earth's surface. The Allegheny Mountains of southern Pennsylvania cross the image in the upper left, and the Susquehanna River flows southeast into Chesapeake Bay. What look like white bumps are a few puffs of clouds. These features are a reminder that you live on the surface of a changing planet. Forces in Earth's crust pushed the mountain ranges up into parallel folds like a rug wrinkled on a polished floor. The clouds tell you that Earth's atmosphere is rich in water, which falls as rain and erodes the mountains, washing material down the rivers into the sea. Mountains and valleys are only temporary features on Earth. They are constantly changing. As you explore the universe, you will come to see that it, like Earth's surface, is always evolving. Take a closer look at Figure 1.3 and notice the red color. This is an infrared photograph in which healthy green leaves and crops show up as red. Human eyes are sensitive to only a narrow range of colors. Range of colors, from X-rays to radio waves, to reveal sights invisible to unaided human eyes. At the next step in your journey, you will see our entire planet, Figure 1-4, which is 12,756 kilometers in diameter. Earth rotates on its axis once a day, exposing half of its surface to daylight at any particular moment. The photo shows most of the daylight side of the planet, The blurriness at the extreme right is the sunset line. The rotation of Earth carries you eastward, and as you cross the sunset line into darkness, you say the sun has set. It is the rotation of the planet that causes the cycle of day and night. Earth's interior is made mostly of iron and nickel, and its crust is mostly silicate rocks. Only a thin layer of water makes up the oceans, and the atmosphere is only a few 100 kilometers deep. On the scale of this photograph, the depth of the atmosphere on which life depends is less than the thickness of a piece of thread. Enlarge your field of view by a factor of 100, and you will see a region 600,000 kilometers wide, figure 1.5. Earth is the small blue dot in the center, and the Moon, whose diameter is only 1/4 that of Earth, is an even smaller dot along its orbit 380,000 kilometers from Earth. These numbers are so large that it is inconvenient to write them out. Astronomy is the science of big numbers, and you will use numbers much larger than these to discuss the universe. Rather than writing out these numbers, as in the previous paragraph, it is convenient to write them in scientific notation. This is nothing more than a simple way to write numbers without writing lots of zeros. In scientific notation, you would write 380,000 as 38x 10%. If you are not familiar with scientific notation, read the section on powers of 10 notation in the appendix. The universe is too big to discuss without using scientific notation. When you once again enlarge your field of view by a factor of 100, figure 1.6, Earth, the Moon, and the Moon's orbit all lie in the small red box at lower left. But now you can see the Sun and two other planets that are part of our solar system. Our solar system consists of the Sun, its family of planets, and some smaller bodies such as moons and comets. Like Earth, Venus, and Mercury are planets, small, non-luminous bodies that shine by reflected light. Venus is about the size of Earth, and Mercury is a bit larger than Earth's moon. On this diagram, they are both too small to be seen as anything but tiny dots. The Sun is a star, a self-luminous ball of hot gas that generates its own energy. The Sun is 109 times larger in diameter than Earth, inset, but it too is nothing more than a dot in this diagram. This diagram has a diameter of 16x108 kilometers. One way astronomers deal with large numbers is to define new units. The average distance from Earth to the Sun is a unit of distance called the astronomical unit, AU, a distance of 15x10 tanma. Using this unit, you can say that the average distance from Venus to the Sun is about 7 AU. The average distance from Mercury to the Sun is about 39 AU. The orbits of the planets are not perfect circles, and this is particularly apparent for Mercury. Its orbit carries it as close to the Sun as 0307 AU and as far away as 0467 AU. You can see this variation in the distance from Mercury to the Sun in figure 1.6. Earth's orbit is more circular, and its distance from the Sun varies by only a few percent. Your first field of view is only 52 feet, about 16 meters in width. After only 6 steps of enlarging by a factor of 100, you can now see the entire solar system, figure 1.7. Your field of view is 1 trillion, 2 times wider than in your first view. The details of the preceding figure are now lost in the red square at the center of this diagram. You see only the brighter, more widely separated objects as you enlarge your view. The Sun, Mercury, Venus, and Earth lie so close together that you cannot separate them at this scale. Mars, the next outward planet, lies only 15 AU from the Sun. In contrast, Jupiter, Saturn, Uranus, Neptune, and Pluto are so far from the Sun that they are easy to place in this diagram. These are cold worlds far from the Sun's warmth. Light from the Sun reaches Earth in only 8 minutes, but it takes over 4 hours to reach Neptune. Notice that Pluto's orbit is so elliptical that Pluto can come closer to the Sun than Neptune does, as Pluto did between 1979 and 1999. When you again enlarge your field of view by a factor of 100, the solar system vanishes, figure 1.8. The Sun is only a point of light, and all the planets and their orbits are now crowded into the small red square at the center. The planets are too small and reflect too little light to be visible so near the brilliance of the Sun, nor are any stars visible except for the Sun. The Sun is a fairly typical star, and it seems to be located in a fairly average neighborhood in the universe. Although there are many billions of stars like the Sun, none is close enough to be visible in this diagram, which shows an area only 11,000 AU in diameter. The stars are typically separated by distances about 10 times larger than the diameter of this diagram. You will see stars in the next field of view, but except for the sun at the center, this diagram is empty. It is difficult to grasp the isolation of the stars. If the sun were represented by a golf ball in New York City, the nearest star would be another golf ball in Chicago. Except for the widely scattered stars and a few atoms of gas drifting between the stars, the universe is nearly empty. In Figure 1.9, your field of view is expanded to a diameter of a bit over 1 million AU. The sun is at the center, and you can see a few of the nearest stars. These stars are so distant that it is not reasonable to give their distances in astronomical units. To express distances so large, astronomers define a new unit of distance, the light year. 1 light year, Li, is the distance that light travels in 1 year, roughly 1013 kilometers or 63,000 AU. The diameter of your field of view is 17 Li. The nearest star to the sun, Alpha Centauri, is 42 Li from Earth. In other words, light from Alpha Centauri takes 42 years to reach Earth. Do you remember that Alpha Centauri is one of our favorite stars? See Pishi for a list of favorite stars. It is in the southern sky, so it is invisible from all but the southernmost parts of the United States, where it occasionally peaks above the southern horizon. If you ever have the chance, you should locate the sun's nearest companion in space. In a later chapter, you will discover that Alpha Centauri is actually 3 stars orbiting around each other. Our favorite stars have interesting secrets. Although stars are roughly the same size as the sun, they are so far away that you cannot see them as anything but points of light. Even with the largest telescopes on Earth, you would see only points of light when you looked at stars. And any planets that might circle those stars are much too small and too faint to be visible. Using indirect methods, astronomers have found nearly 200 planets orbiting other stars. In Figure 1.9, the sizes of the dots represent not the sizes of the stars, but their brightness. This is the custom in astronomical diagrams, and it is also how star images are recorded on photographs. Bright stars make larger spots on a photograph than faint stars. The size of a star image in a photograph tells you not how big the star is, but only how bright it looks. In Figure 1.10, you expand your field of view by another factor of 100, and the sun and its neighboring stars vanish into the background of thousands of other stars. The field of view is now 1,700 Li in diameter. Of course, no one has ever journeyed thousands of light years from Earth to look back and photograph the solar neighborhood, so this is a representative photograph of the sky. The sun is a relatively faint star that would not be easily located in a photo at this scale. What you do not see in this photograph is critically important. You do not see the thin gas that fills the spaces between the stars. Although those clouds of gas are thinner than the best vacuum on Earth, it is those clouds that give birth to new stars. Our sun formed from such a cloud about 5 billion years ago. You will see evidence of star formation in your next field of view. If you expand your field of view by a factor of 100, you see our galaxy, Figure 1.11. A galaxy is a great cloud of stars, gas, and dust bound together by the combined gravity of all the matter. Galaxies range from 1,500 to over 300,000 Li in diameter and can contain over 100 billion stars. In the night sky, you see our galaxy as a great cloudy wheel of stars ringing the sky as the Milky Way, and our galaxy is called the Milky Way galaxy. Of course, no one can journey far enough into space to look back and photograph our home galaxy, so the photo in Figure 1.11 shows a galaxy similar to our own. Our sun would be invisible in such a photo, but if you could see it, you would find it in the disk of the galaxy about 2/3 of the way out from the center. Our galaxy, like many others, has graceful spiral arms winding outward through the disk. You will discover that stars are born in great clouds of gas and dust as they pass through the spiral arms. Ours is a fairly large galaxy, roughly 75,000 Li in diameter. Only a century ago, astronomers thought it was the entire universe, an island universe of stars in an otherwise empty vastness. Now they know that our galaxy is not unique. Indeed, ours is only one of many billions of galaxies scattered throughout the universe. As you expand your field of view by another factor of 100, our galaxy appears as a tiny luminous speck surrounded by other specks. This diagram includes a region 17 million Li in diameter, and each of the dots represents a galaxy. Notice that our galaxy is part of a cluster of a few dozen galaxies. Galaxies are commonly grouped in such clusters. Some of these galaxies have beautiful spiral patterns like our own galaxy, but others do not. Some are strangely distorted. One of the mysteries of modern astronomy is what produces these differences among the galaxies. Astronomers have found some important clues and have developed a fascinating theory. If you again expand your field of view, you see that the clusters of galaxies are connected in a vast network. Clusters are grouped into superclusters, clusters of clusters, and the superclusters are linked to form long filaments and walls outlining voids that seem nearly empty of galaxies. These appear to be the largest structures in the universe. Were you to expand your field of view another time, you would probably see a uniform fog of filaments and voids. When you puzzle over the origin of these structures, you are at the frontier of human knowledge. The first hurdle in studying astronomy is keeping a proper sense of scale. Remember that each of the billions of galaxies contains billions of stars. Later you will see clear evidence that many of those stars have families of planets like our solar system. And on some of those planets, liquid water oceans and protective atmospheres may have sheltered the spark of life. At least a few other planets may be inhabited by intelligent creatures who share our curiosity and our wonder at the scale of the cosmos. Let's break down the vastness of space into a fun, mind-blowing lecture. Here's your cosmic journey, scaled down to fit our understanding. Starting point, Earth and you. You live on Earth, spinning daily, orbiting the sun yearly. Picture our planet's rotation. Sunrise and sunset, day and night, all within your personal experience. Our solar system. Earth's part of a family of planets: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and, well, Pluto's status is a bit of a debate among astronomers. These planets orbit the sun in elliptical orbits. For instance, Mars is about 15 AU, astronomical units, from the sun. Key players: Sun 109 times Earth's diameter. Planets Mercury to Neptune, each with unique orbits. Moon, a fourth Earth's diameter. Scaling up, stars and galaxies. The sun's just one of billions of stars in our galaxy, the Milky Way. Milky Way's massive, about 75,000 light-years across, hosting over 100 billion stars. Distances. Nearest star, Proxima Centauri, 42 light-years away. Light-year distance light travels in a year. Fast, right? At 300,000 kilometers, that's huge. Beyond our galaxy. We're not alone. Billions of galaxies float in the universe, clustered in filaments and walls. These structures are the universe's largest formations, galactic neighborhood. Andromeda Galaxy, 2 million light-years away, our closest galactic neighbor. Galaxy clusters and superclusters form the cosmic web, measuring cosmic scales. Astronomers use an AU for solar system distances, Earth to Sun, L1 AU, the light-years for interstellar distances across galaxies. Metric system for simplicity in calculations, km, meters. Other Earths out there. Many stars host planets, and though we've found fewer than 200 exoplanets directly, planets are likely common. Maybe there's an Earth-like world orbiting a distant star, waiting to be discovered. Chapter 1 Wrap-Up. From Earth's rotation to galactic superclusters, our universe is layered with wonder. We've journeyed outward in steps of 100, scaling from campus views to cosmic expanses. What's your next question about space, Jonathan? Want details on exoplanets, galaxy formations, or maybe how to spot constellations?